Alright, vectors and components. So when we talk about a resultant vector, we mean basically the overall vector. And the components represent the x direction and the y direction. So here's a vector which has a 12-meter x component to the right and a y component of 5 upward. And I want the resultant, the overall length of this vector. So this is simply a matter of using a Pythagorean theorem. So we can say that 12 squared plus 5 squared equals c squared, if we call this c. And so 12 squared is 144, 5 squared is 25, equals c squared. So c squared equals 169, and so the square root of that is 13. So the length here is 13. That is the resultant of this here. So a 12 to the right and a 5 up has a resultant value of 13. Now we are given sort of the opposite situation. I am given the resultant and an angle, and I want to find out how much is it to the x direction, how much is it to the y direction. Now if this were done on graph paper and drawn to scale, you could theoretically just measure these lengths, but there's always some error in that, and it's not very often you're going to come across that. So we're going to use some trigonometry. And the only real thing we have to remember from trig is the SOHCAHTOA, this sort of mnemonic device. And this mnemonic device says that sine equals opposite over hypotenuse, cosine equals adjacent over hypotenuse, and tangent is opposite over adjacent. What does this mean? It means that if I take the sine of 55 degrees, it is equal to, if this is the angle, the opposite, which here is y, divided by the hypotenuse. If this is the right triangle, the right angle, the hypotenuse is opposite that, so over 80. And it means that the cosine of 55 degrees in this situation is the adjacent leg, this one, x, over the hypotenuse 80. And this is enough for me to solve for y and x. I don't actually need tangent. So that means y equals 80 times the sine of 55 degrees, and x equals 80 times the cosine of 55 degrees. So make sure your calculator is in degree mode when you go to do this. And so I get a y component of 65.5, I'm rounding it a bit, and an x component of 45.9. And this should make some sense that the y component's larger, because if you look at it, 55 degrees is more vertical than it is horizontal. And because this vector is pointing up and to the right, I'm going to make sure these are both positive components. I couldn't get that from the trig, but then I just sort of apply it afterwards. And if I really want to check, if I use the Pythagorean theorem on this number and this number, I will get 80 for the hypotenuse. It should check out. Here is another problem, same thing, break down their components. And the reason I demonstrate this one is so you see that sine does not always correspond to y. So in this situation, sine, if I call this x and I call this y, the sine of 15 degrees equals the opposite, in this case x, over the hypotenuse 60. And the cosine of 15 degrees equals the adjacent, in this case y, over the hypotenuse. So if I do the sine 60 times sine of 15, I get the, excuse me, that was x. The x component is 15.53, and the y component, 60 times cosine of 15, is 57.96. However, this is where we have to think for a second. If the vector is going down and to the right, the x component is positive because it's going to the right, but the y component is negative because it's moving downwards. So we just have to apply that negative after. So these are the components of this particular vector. Lastly, sometimes you can be given the components and you have to find the angle. So this is a little bit different. In this situation, the angle, I know this is the opposite and this is the adjacent. So here's one where I'm actually going to use tangent. So the tangent of this unknown angle, which we'll call theta, equals the opposite 8 over the adjacent 30. And I want to solve now for this angle. Now it's not just a matter of we can't divide by tan and cancel tan. That's not how trig works. So first, if I do 8 divided by 30, I get 0.267. So the tangent of some angle is 0.267. So you could try trial and error and hit tan of a bunch of different angles until you hit this number, but that would be kind of silly. So instead what you're going to do is we're going to use another operation called tan inverse. And what tan inverse does is say tan inverse of 0.267. If you plug this in, it will tell you the angle. So it basically does this process in reverse for you. This button here, tan inverse, it's usually the same button as tangent, except you have to hit a function key to get it. So if I type tan inverse of 0.267, I get an angle of 14.95 degrees. And then to double check that, I can take the tangent of this from my calculator, and it should give back 0.267. So that's one way you can check it. And this actually looks reasonable, about 15 degrees. I didn't totally draw this to scale, but it's in the ballpark. So always make sure your answer makes sense. If you had an answer that didn't make sense, like 92 degrees, you know, go back and double check your answer. And again, make sure your calculator is in degree mode for this. So that is vectors and components. Make sure you have a firm understanding of this before you move on to anything else, because everything else depends sort of on this. So until next time, I am Derek Genova. Have a delightful day.